So this is the 16th session of the part 1 of this series of lecture. So today the topic will be the application of phase analysis we discussed last time. So we will start with the idea of coupling. I have shown you some applications of phase, and now let's talk about coupling. So I want to use a few minutes to quickly introduce an algorithm called synchrogram to detect coupling called N versus M coupling. So suppose I give you two signals. Okay, this is a slowly varying, this is fast varying. I want to ask the question about, is there a coupling between these two signals? And if there is a coupling, which kinds of coupling is there? So what we do is very simple. First, we evaluate the phase. Okay, we evaluate the phase of this signal. And you see we plot from 0 to 2 pi, 0 to 2 pi. Everything is mod by 2 pi. And then, once we get to the phase, we fix an, give me a second. Then, we fix an angle, theta, that we have interest. We fix it. And then, once we fix it, we know where the phase will hit this fixed angle. So we determine a sequence of times, T1, T2, T3, and so on. So there will be detectors. That will be our detectors. Okay, of what? Of the low frequency component in the following sense. For low frequency component, we first determine the phase. So we get a phase, but now we say we want to check if there will be any coupling in between the low frequency and high frequency, in the sense that every two oscillations in the low frequency component, we have something similar in the high frequency. So we take M to be 2. Okay, that is the M we can fix. So we fix M to be 2, so that it will go up to 4 pi for 2 oscillations. And over 4 pi, we detect the location using the detector T1, T2, T3. We detect all those timing, and we can generate a plot on the right-hand side. And this plot is read in the following way. You have different timing, T1, T2, T3. That will be the detector. And the y-axis point associated with Ti will be the phase at Ti of the lower frequency component. But we take M to be 2. So that is what I put on the right-hand side. Phi2 is the phase of the slowly varying component. Okay, and we detect over time Tk, which is determined by the high frequency component, and it is mod out by 2 pi m. In this case, m is 2. And then we divide it by 2 pi. Then will be the point of the phase of the slowly varying component at time tk. Okay, so if there is an N versus M phase synchronizations, then we will see N horizontal lines. In this case, we have 1, 2, 3, 4, 5 horizontal lines. So this tells us that we have detected a 5 versus 2 coupling. So a slow signal is observed in accordance with a fast signal. This should be, well, A and E. So that is the algorithm. Very simple. But what then? We now get a plot, okay, and a set of points on the plot. What should we do? Then we can do some quantification. We can quantify what the distribution looks like and use it to determine the so-called coupling strength and so on. This is the quantification, and we'll introduce this in a bit. That is overall the synchrogram algorithm, and this synchrogram tells this is called synchrogram. Okay, and this is the original literature published in 1999 in Nature. So this synchrogram is actually a very simple idea, a generalization of a very simple idea called phase stroboscope. Okay, and I'll use this very short video to demonstrate what this phase stroboscope means.
Line painted on it.
So there's a.
I want you to think of this as a clock. Turn it on. It's a high-speed clock. It's moving too fast where you can see the hand. But with the
and you have a light.
Stroboscope, you'll be able to see
and the light will flash very, very quickly. And now, if it starts to flash, you can see the hand to change it.
What I want to do is make it appear like there's just one image of the hand, and that it's moving as slowly as possible.
So you change the flash speed.
I'm decreasing the frequency now.
If the frequency is adjusted correctly,
I'm down now to 3,200 flashes per minute, and now 3,100 flashes per minute. Now you notice that the line first appeared to be going one way, and then stopped and go the other way. Let's see why that's happening. First of all, if I could adjust this so that the line seemed to be stopped.
Yes, it stopped.
It's pretty nearly stopped now. I'll leave it like that for a moment. It's still moving, of course. Okay. If it were completely stopped or appeared to be stopped, then what that would mean would be every time this light flashed once, the line or the disc went around once.
Yep.
So this flashes, you see the line in a particular position. The next time this flashes, the disc has gone around, but the line is in exactly the same position. That's the only time you see it, so it appears like it's stopped. Now, if it appeared...
Oops. So that is the very basic idea of phase stroboscope. And from this phase stroboscope, you can see it is able to detect some kind of company. And the synchrogram is a generalization of this idea. And if you have interest, you can go to the YouTube video. That is it has a full version. I only showed you a very small clip to show you the basic idea. Okay, so this is another example so that you have a better idea. So you have a respiratory signal. This is a respiration. This is the simultaneously recorded ECG signal. And from this ECG signal, you can, again, as what we mentioned before, you can determine the phase. You can determine the phase, and you fix an angle theta. And this theta in this situation is the p value. The p wave. So you use p wave location as the theta, and you detect the low frequency component, which is respiration. So you can see if you go among the if you detect the phase using the p wave of the ECG signal, you can get all these values, and you generate the synchrogram. Now you see there are three lines, and what you do is you just take one. So this is 3/1 company. That's what you can observe immediately. And we can use it to quantify cardiopulmonary coupling. So that's a respiratory signal. This is the ECG signal, simultaneously recorded one. But this time, we will not quantify the coupling between respiration and the ECG. This time, we will quantify respiration and the heart rate. And what we do is, from the ECG, from the heart rate signal, we can determine the phase, and from the respiratory signal, we can determine the phase. And from the phase, we can then run the synchrogram and generate this plot on the right-hand side. So you see, there is one curve, right? One line, one vertical, one horizontal line. So it tells you that there is a 1-1 coupling. And you can zoom in to see some beautiful behavior. And in this case, we can easily quantify the cardiopulmonary coupling strength by using this definition, which is very simple. We try to quantify if the distribution of the point is precisely located over a vertical line, because if the distribution of psi Ti is not distributed over a vertical line, then this psi value will be varying, and the averaging will be smaller than the desired value, so that this value will be smaller than 1. So this value will be always positive, greater than 0, but always be bounded by 1. And the higher the value is, the stronger the coupling is. So this is a very simple quantification of this coupling using synchrogram. And you can see another example. This is a good coupling case. And this is a coupling between heart rate and respiration. And this is another example, which is a bad coupling. You can see this is a phase. This is a phase of heart rate, but the distribution is kind of chaotic. There is no no horizontal line and so on. So if you quantify the index, it is 0.35. It is considered a bad coupling. Okay. So now, if you recall, we spent some time discussing the definition of coupling of phase using synchronous squeezing. And why so? Because we want to get rid of the impact of the wave shape function and so on. And now, let's see how it impacts the clinical application. So here, we have several different kinds of respiratory signals: impedance, entitled CO2, and airflow. And they are all recording our respiratory dynamics by using different sensors. We want to see how they are related. So what we do is we take each respiratory signal and we evaluate the CPC, the cardiopulmonary coupling of the synchrogram using the previous definition I showed you. But when we define the phase, we use different approaches. On the top row, we use just bandpass filter and Hilbert transform. The middle one is the synchronous squeezing transform I showed you before. In the below, this is continuous wavy transform, which I haven't told you about continuous wavy transform, but this is an algorithm that is commonly used in practice, which we'll come back to discuss later in a later part of this in a later session. And now there are 9 subplots, and they are about the Bland-Altman plot, which shows the agreement rate of 2 different sensors or 2 different instruments. And this BA plot was considered maybe top 10 algorithms in the 20th century. It has been cited maybe more than, I don't know, 200,000 or something, crazy number of citations. People use it again and again. I don't know, I don't remember a precise number, you can check it. Okay, whatever it is, in the x-axis, you just show the mean value, A plus B, of 2 measurements, 2 instruments. You just evaluate the mean. And in the y-axis, you plot the difference. The ideal situation is the 2 instruments are perfectly equivalent. Then, no matter what A and B are, you should see the difference will be 0. So you should get a perfect horizontal line at 0. That is the perfect situation. But if the agreement rate is very bad or not ideal among 2 different instruments, then you will see something very sporadic. Now you can see the result. If you use Hilbert transform, the traditional approach, then the disagreement rate is high. But if you use synchronous squeezing, the agreement rate is high. But if you use continuous wavy transform, it is in between. So it tells you the benefit to consider synchronous squeezing transform combined with the phase function I showed you before, because it is more immune to the wave shape function that encodes the nature of sensors. And now let's take a closer look at these different algorithms. We have airflow signal, impedance signal, entitled CO2. Impedance is RSP. You can see that they are oscillating with different oscillatory patterns. The wave shape functions are different. If you use continuous wavy transform, usually you have a fixed band. Okay, and this is the reconstructed component that for you to evaluate the phase. And this is Hilbert transform, which they look similar but still different. But if you use synchro squeezing transform, as I told you, we'll use the band time varying band limited reconstruction. That is a reconstructed fundamental component for us to define phase. But if you use the time varying band pass for continuous wave transform, you can still do it, and this is the result. This is the result. So you can see adaptive band pass of continuous wave transform is similar to the synchro squeezing transform band pass. Okay, but if you use fixed band pass of continuous wave transform, it is more similar to the traditional Hilbert transform. Why? Because we have to recall we have to adapt us to the time varying frequency, time varying amplitude, the wave shape function, all need to be considered. If you do not respect this fact, then you are not be able to recover the fundamental frequency, so that the phase definition is a bit weird. And once you get to the decomposition, for example, this is decomposition using continuous wave transform with fixed bandwidth. This is fundamental component, and that will be the phase. Okay, that will be the phase. And now you can try to quantify the agreement of the phases of different channels. Now you see, this will be the comparison of these two channels. This will be the comparison of these two channels. This will be the comparison of these two channels. You can see they may look agree, but a lot of fluctuation. However, if you use the synchro squeezing transform as I introduced, then the agreement rate is quite flat. It's quite flat. So this is one way to convince you the necessity to take the time varying frequency, time varying amplitude, and the wave shape function into account. So that in the very end, although you have different channels, different respiratory signals, and these three usually can be recorded in the hospital using more expensive, bulky equipment, and the signal quality is usually better. But at home, usually we can only have lower quality respiratory signal. The signal quality is not only low, but it is, but also kind of, less reliable. But we can extract almost equivalent information if you respect this kind of sensor-dependent wave shape function information, so that you can transfer the information or the research result you get in the hospital to the digital health home care environment. Okay, so there is a clinical study as an example. I will not go into details, but if you have interest in clinical applications, that is the paper you can check. We collected some patients with chronic obstructive pulmonary disease, COPD. And what we did was we tried to quantify the coupling using synchrogram and classify the subjects into different classes. And we want to observe if a patient with COPD will have some inclination to develop something bad. And in this study, we just reported something very, very simple, but you can already see something very interesting. For example, the synchrogram index or the CPC index is directly related to the distance or this distance saturation product. Okay, so the clinical interpretation, I will skip the clinical interpretation, but it tells you that by doing this kind of analysis, the coupling, the phase can help you to define a beta coupling index, and this beta coupling index could provide useful information, potential information. And yeah, this is some kind of ongoing project, and for clinical parts I will skip. The next application will be so-called decoupling among harmonics. Decoupling among harmonics. Before, what I told you was about coupling in between two different channels. But now I want to discuss the coupling or decoupling in between, in one channel, but we want to study the relationship among harmonics. And what does it mean? Okay, the data that we will discuss will be this lower body negative pressure study. This is the study that simulates blood loss, acute hemorrhage. So you start from baseline, okay, then you don't do anything, and then you have leg rest test. You rest your leg so that the blood inside the leg will go to your central part. This will simulate hypervolemia. And we come back to baseline, and then we started to run this lower body negative pressure. And what is it? You have a body, this is your upper body, and you will have your lower body sealed in a chamber. And the chamber, we will suck the air, make it vacuum. Okay, and because of the negative pressure environment in the chamber, the blood that enters your legs will be stuck there, and that will simulate central hypovolemia, or simulate acute hemorrhage. And this is the currently so far the safest approach to simulate this kind of hemorrhage and to study hemorrhage. And for example, if it is minus 15, it is roughly 200 milliliter blood loss. And if you go up to minus 60, that is roughly 1 liter blood loss, and so on. And then you come back recovery and come back to baseline. Okay, and to study this data in this experiment, let's recall this fact. Last time we discussed, or not last time, but in previous session, we said that in general, one wave shape is not sufficient to discuss the real world biomedical, about biomedical signal, in particular oscillatory ones. Because the traditional wave shape function, when you have only one wave shape function, what you are doing is you have some kind of stretching, dilation of one wave shape, and then you stretch it. You scale it, okay? And you want to keep A, the amplitude modulation, to be slowly varying, and the instantaneous frequency to be slowly varying. So this idea, this model cannot well capture this behavior, which has sudden change in wave shape. So we discussed this generalized adaptive non-harmonic model, and the basic idea is nothing but return the model in the Fourier series, and in the Fourier series mode, you try to do generalization by making everything time varying, so that you capture time varying wave shape function, and we still call this the harmonics and so on, fundamental component. Yes, and we usually assume that the wave shape function has mean zero, if you recall it. Good. Now let's take a closer look at the impact of the phase information. Okay, so this is the wave shape function of a real PPG signal cardiac cycle. And what I do here is I rewrite this cycle in this Fourier series. So you can see there is alpha 2, this is the phase, how I shifted the phase, alpha 2, and there's C2, the strength, the amplitude. Now if you pay attention, you see if the C2 is fixed 0.4, and you just change the phase of the second harmonic, then you can see that the morphology changes dramatically. Okay, but if you change the amplitude from 0.1 to 0.8, actually the morphology changes, but not dramatically. Not too much, but it does change. It tells you that the wave shape function actually depends on the harmonic and But it is the phase that plays maybe a more important role. Okay, and there is a, well, the time domain information, the morphology of the shape, and the phase, they are very nonlinearly related. So, yeah, we can only say it up to now. We need more research. Because the Fourier transform in the time domain and frequency domain, there are too much nonlinearity. But anyways, you can already see something very rich here. So if we use the generalized adaptive non-harmonic model I showed you, and you do this decomposition, okay, this is the PPG signal, and you decompose into the first fundamental component, second harmonic, third harmonic. Very good, right? Just like cosine with some amplitude modulation. Good. Now, we know that all these components are actually from the reconstructed one, and the reconstructed one are in a complex space, in a complex form, as we discussed before in synchro squeezing. Okay, so you can see, oh, in the complex domains, they have some kind of nice like winding, well, not winding, but circle. Okay, so far so good. But now let's take a look at what I meant by coupling. What I want to say is, look at the fundamental component and the second harmonic, the first and second harmonics. You can see that phi1 and the phi1 and the phi2, they obviously are not on the same order because the second harmonic obviously oscillates faster than the first harmonic, right? But if you recall the definition of adaptive non-harmonic model, actually they have some relationship. So what I do now is I just take the phi1, the first fundamental component space, and I multiply it by 2. That is, I double the frequency of the fundamental component so that it is on the same order of the second harmonic. Okay, and I do the subtraction. And if you take a look at this difference, you see the phase changes from -3.5 to -0.5. And this is, I should have a picture to show you. Actually, this is this phase difference actually describes the ear, the dichrotic notch. You will see the dichrotic notch here, but not the dichrotic notch here. Okay, but yeah, whatever, it is over this region. So it tells you that the phase discrepancy between harmonics actually captures this kind of very delicate small time domain information. And let's take a closer look. This is the PPG recorded from ear, okay, and this is the baseline, leg resting test, neck tube pressure -15, and so on. You can see the morphology changes, right, very clearly. And that is the fundamental component and the second harmonic. Now, as I told you, I will double the frequency of the fundamental component and compare with the second harmonic. Now you can see the phase discrepancy. This becomes more synchronized, right? And this more desynchronized. And that is the phase difference that you can see. Okay, so now what I do is I will quantify this difference and call it delta phi k. And I also have delta ak. And I will consider all this as indices. I want to quantify what's going on. And what I show you above, they are the amplitude of the harmonics at different phases. And you can see that fundamental component drops, but the second harmonic amplitude is very, very constant. And we still don't know why. And the third harmonic drops in the return. So there must be something interesting inside. We still do not fully understand. But anyways, this is ongoing, and the paper is in Journal of Clinical Monitoring and Computation, whatever. Yeah, and that is the dynamics. Okay, but this is more clinical. I'll just show you the results. It says that using early PPG, ear PPG, we can early predict hypovolemia. Okay, and that is the clinical result. And that is a classification. We can use those indices to quantify if a patient, or to predict if a patient can tolerate more blood loss or less blood loss. And the application is obvious, right? In the battlefield, you want to have some working blood bank. However, it tells you that you can really predict the year, really predict this kind of tolerance from ear PPG in the very early stages. Okay, you can get a very nice ROC. That is it for this session. Thank you very much.